I told you on the phone the other day, is where I'm going to take this thought experiment, and I'm going to ask you all to use your imagination, meaning that no, I'm not saying this is real, not exactly, but I want you to use your imagination, and the venue for this thought experiment is going to be some place that we've all been indoctrinated to believe is there, and even understand kind of the physics of it a little bit, right? Because of our Star Trek and our Star Wars and stuff like that. So this thought experiment is going to take place in outer space, okay?
So just listen to where you're going. Listen where you're having to start this off at. And I didn't make this video to rag on you or nothing like that. I just want to refine the other side of the argument a little bit and point out, how you even see it and even talk about it. But I want to point out, without space, they have no model. Without outer space, without gravity, they have no model. They have no sphere. They have to have gravity. Okay? They have to have it like that, or they don't have a model. Our model does not require that, because there is a limit. There's a firmament, whatever it may be. It keeps in the pressure. Okay? And you even spoke about the quote unquote microgravity up there in the rockets we have actually seen, the Go Fast rockets, and I'll play that later on in the video. But I understand exactly what you're saying, and it's tempting to want the downward bias, but it all follows the rules of density and relative density. Okay, I don't have to go over that. You understand that the weight of anything is relative to the medium that it's in, and vice versa. So, but I just want to point out a couple things here.
So imagine yourself, and remember I said imagine, all right? Imagine yourself in the middle of space, and there's no bodies around you, no stars, no heaven. You're just there in your spacesuit, kind of like a scene right out of Gravity, right? And you're just...
I'm going to skip through some of this, but I'm pretty sure everybody who's watching this video has seen that. But you're having to imagine things, and they have to, and I've spoke with some of the leaders in the globe model debating, and they say pretty much that the gravity equations only apply like off the planet Earth to figure out the G, M1, M2 over R squared over distance squared is to pretty much get your relative weight, like your weight on the moon, how much you'd weigh, how much gravity there is. But just here on Earth, we don't need that equation. We don't need F equals ma. It's basically weight equals mass times acceleration. So basically what the force is you walk outside and tell me what's accelerating. Nothing's accelerating. Here's the force. Okay, we still use 9.8 meters per second squared. Okay, but if you force a solid out of equilibrium up into the air and in the air, if you force a solid up in the air, then it's going to come back down to equilibrium. Okay, but the force is you forcing it up there. Okay, that's the force. Or if you force a balloon or a beach ball underwater, that's the force. It's not a buoyant force bringing it back up. The force is getting it down there. It takes energy. It takes force. Okay, so
the oil sits on top of the water. Why is the oil on top? The answer is intuitive. Heavy things sink down and light things float up because gravity pulls on the heavy things harder. But what happens when the G-force goes away?
He just said heavy things go down and light things go up because gravity pulls harder. Dude, just stop and please think about that for a second. It's a slap in the face, really. Contradiction.
Well, if we don't have it down, we don't have it up, and so who knows what'll happen. Carthage College's microgravity team explored what happened in August 2013 with some help from NASA. To figure this out, we need
Now, just real quick, that should be a red flag right there. You know, so you can see where this is going.
two things, a density tower and a zero-G environment. The first item is pretty easy to obtain, and we don't need to use only two fluids. Some enthusiastic scientists have created these density towers with 9 different fluids.
Okay, and this, of course, is the density tower that Sleeping Warrior likes to use with the dish soap, water, everything, and the cherry in between and all that stuff. And as you can see, you know, here on Earth, with a downward force, the layers, the honey, corn syrup, and everything layer perfectly. Okay, so let's continue on.
And they behave pretty well as long as they aren't jostled too much. Here's a tower with 3 immiscible.
Hear that? As long as they ain't jostled too much. Okay, they behave pretty well. Not great, but pretty well. As long as they're not jostled. So they don't even behave well if they are if they're not jostled. But they do behave pretty well if they're not jostled. You jostle them, and that's it, dude. Then it's not even going to behave worth a shit at all. You've obviously never seen one in real life. That's not a shot. That's just probably a fact.
Fluids, vegetable oil, water with blue food coloring, and some leftover FC72 we had in the lab.
And some what? Some leftover FC72. Can't we just use normal, over-the-counter, regular fluids that we're all familiar with? Why do they have to use some space antifreeze bullshit? Something that nobody can repeat. And it gets worse, and I'm going to point it out.
FC72 is an experimental spacecraft coolant. It performs the exact same job as car coolant, just in space. Links in the description for more about FC72. The zero-G environment is a bit harder to come by.
This shows you that they're full of shit when they're talking about in space. Okay, if they need coolant in space, okay, when, you know, the video that I'm about to show, the one you made, Bob, with Arrow and them, show how cold it gets up there and the ice forming on the rockets. Why would they need coolant up there? In real life, I don't think they do.
Thankfully, Carthage College had been selected by NASA to perform a different experiment with FC72 in zero-G. To perform zero-G experiments, NASA uses G-Force 1, the microgravity plane. To make zero-G, G-Force 1 flies in a parabolic shape. That is, they go up in the air at full speed and then cut the engines to fall to Earth before turning the engines back on and repeating the whole process over and over again. The Carthage College microgravity team took the 3-fluid density tower aboard G-Force 1 when they went to Ellington Field.
The density tower team, the microgravity, the density tower team, got a whole team of some bitches, and space fluid for a simple demonstration. And instead of showing it simple, look at to me, you know, it's deception, but I'll let you see and be the judge.
In Houston, Texas, to perform their FC72 experiment for NASA. In the footage that follows, you'll mostly see John Robinson and Eli Favela handling the name. Why? Called out. Tip 2. Watch your feet. Of the flight is
It's got different liquids, different densities. So right now we're in the microgravity, so you can really separate. You have FC72.
So they're in hypergravity right now, or whatever you want to call it. Okay, they're hauling ass. Okay, or else if you shake that thing at all, it's gonna mix up. But it's pinned down. In my opinion, if you put some pressure in that thing and you hold it still, it'll still level out. And if you watch carefully, you'll see it trying to level out. If he just quit shaking the shit. But watch.
Water and vegetable oil. Then as soon as we hit zero, as soon as we go into microgravity, well, you'll see. Zero. Red science!
Whatever that clump of shit is, but he keeps taking it starts to settle out, and then he moves it toward the camera. starts to settle out, he moves it toward the camera, and it still settles out a little bit at the end before they get their gravity. Now, why wouldn't they just show it? You know, for this to be an honest video, this is like the feather in the bowling ball with the Brian Cox. It's just clips, cuts, instead of showing control, showing him on the ground, shaking it up and how long it takes. It's just not honest. And if you're not honest, then 9 out of 10 you're hiding something, and that's my opinion. Now, I could be wrong, but I'm calling it how I see it.
That was a bit tough to see as John started to float away with the tower, but did you see the way it oozed? Let's see it on the next parabola, once John has strapped himself down a bit.
1, 0. Not separating at all. It's just sitting there floating. All of it mixed up. Yeah, just a little bit.
Maybe that's because he just shook it up, upside down, right side up, upside down, right side. He just literally shook the damn thing up. The space coolant.
And then we go into regular gravity.
Now, why didn't they wait? And they could have waited, and I see the water go to the bottom, but they could have waited to see how long it takes to settle out. But I bet you it took a little longer than it should have, so they cut. That's my opinion.
Did you see how the fluid didn't separate out like it did in normal gravity and hypergravity? And did you see the different color blobs just cycle around?
To me, man, that's manipulation, man. That's my opinion. So I just want to, and here's another thing. The main point of this, Bob, is that if you're free falling, you are in disequilibrium. Okay, you force everything up there in the plane. You need all that energy, momentum to get yourself up there. That is the force. Okay, the force is pulling everything out of equilibrium. Okay, nature acts on equilibrium. Everything in nature acts on equilibrium. Disequilibrium is a force. It takes a force to create disequilibrium, in my opinion. But one thing I've noticed is that everything acts on equilibrium and entropy. So if you take something and you force it up there, and then it just starts free falling. It's in disequilibrium. So why would we even expect it to sort itself out? It's still in disequilibrium. It's free falling. So that's the density disequilibrium, the relative density disequilibrium argument, and it makes 100% sense. 100% sense, and I think you've recognized it at times, and just something won't let you let go of that force. But maybe this video will help.
Watch it one last time as John swishes it up going into 0G.
0, 5. Feels like the pump's still working. Oh, that's pretty cool swirling in there.
It's separating out a little bit, man. But besides that, we wouldn't need, in our argument, we wouldn't even expect it to until it got back into equilibrium. And the free fall would not be equilibrium. So.
My earlier assertion of what I said that I wanted to prove here is that to show without the so-called force acceleration effect phenomenon of gravity, the concept of relative density and buoyancy are rendered moot. Okay? You just saw it. We have removed that downward force, and now all of a sudden density and buoyancy don't cut it anymore because the liquids are not separating. There you have it, guys. There is your nuke. And I have more examples than just this. I have many more examples, but I want to hear your comments on this.
So that plane isn't falling? The plane is just floating in space?
It's falling. It's falling
okay,
essentially.
So it's falling.
It's falling, and it's essentially eliminating the gravitational force, much like we did in the space thought experiment. The exact same thing happened.
It's just a falling frame of reference. The zero-G plane is not in zero-G. Anybody who tells you that is completely confused. It gives the illusion of zero-G, and he mixed up the density tower. The very first thing he does is mix it up. I'll go do that right now. I'll grab a glass of those things. I'll have them separate out, and then I'll tip it upside down and mix it and then show you. Look how it's swirling around and not separating out.
Yes, he mixed it up for a reason, to show you that.
And here's your own boy telling you, man. Common sense, brother. Common sense. And you keep talking about this force. Once again, the force was needed to get that plane up there, to get the density tower up there. Okay? To get it out of equilibrium. Okay? It's free falling. It is not in equilibrium. When it hits the ground, it'll be back in equilibrium and it'll sort out. But yeah, man, it's right there in front of your face. But you know, I'm just trying to show you the actual argument for the other side of the argument, man. Oh, one other thing. If you start on the ground, all you need is relative density disequilibrium. There's no buoyancy. It's all relative density disequilibrium. If you start in an imaginary medium that they've never proven, okay, then you need gravity for free falling. Okay, start on the ground, relative density disequilibrium. Start in space, gravity.
On that video there, when it's stopping to the spin, it looks like the Earth itself is getting flatter and flatter as it goes up.
Yeah, and I don't correct its lens. This is a fisheye lens, and I didn't correct it. I leave as original it is. Okay, so that keep that in mind. But right now, supposedly this rocket reached the 120 kilometers. They go into this microgravity, so they cut that part of the video, and they only show us when it's going to re-entry. But something that is, interesting to take into consideration is that, first of all, we have liquid stick to the side of the rocket up there. With the super thermosphere temperature, it's a little strange, because after all, we never see supposedly the spacewalk showing us experiment that the astronauts say, I'm going to release water right now in outer space to see what happened. Nobody showed us. And that will be the most unvaluable experiment out there. What happened with liquid in the vacuum of space? Why they don't show that?
Well, great question. Great point.
So we have or fire trying to start fire up there, whatever. But we have this kind of not just liquid. It's like ice on the side of the rocket, and then we have this behavior like it's like floating. It's not in microgravity or some kind of levitated behavior.
It's like a buoyant behavior. Like it's
God, it's right there, Bob. It's right there. You're even talking about it, man. We don't need gravity if there's no deep space or outer space the way described to us. That's why they need the gravity. They have to have the gravity for the sphere. Okay? If there's a limit up there, which you spoke about and you even speak about on this video, some type of firmament or layer, then it's all buoyancy and density. We don't need gravity. Okay? They only need gravity to explain the motions of the heavens and stuff the way the heliocentric model does. The flat Earth model does not need gravity. And I mean, you're looking at it, you're seeing it, you're talking about it, man. It's right there. I just wanted to point out, go a little further in depth about our side of the argument, because I know you got an open mind. So
bobbing up and down, yeah.
Exactly. And the other thing that's
And then
crazy,
the sudden change, right?
yes, is how it's self-auto-oriented after passing through this state of the fluidity.
Yes.
Because right now the rocket is.
This is that Brian Mullen made the exact same observation, and so did I. That is astounding. You know how it does it. It reorients itself, like something is literally manipulating it, like it's floating. Really?
Yes.
It's
Yeah. So you
Imagine that.